Michel Zakharia received his BE degree in petroleum engineering from the Lebanese American University in 2019. He also received an MB degree in mechanical engineering from the American University of Beirut in 2022. His current research focuses on building energy simulations and is currently employed as a full-time research assistant at the American University of Beirut. Please welcome Mr. Zakharia. You have the 15 minutes to present your work. Thank you.
Hello everyone, and thank you for coming to see my presentation about the assessment and enhancement of thermal comfort in the Makassed schools, particularly in Beirut. My work was done under the supervision of Professor Arami Redian and co-advised with Dr. Aysam Laiz during the whole of my master's thesis. First, I will start by introducing the problem at question, which is related to thermal comfort. Then I will go out and skim over the literature review. Then I will present the problem, the methodology, and the results to finally wrap up with a conclusion. As an introduction, thermal comfort is a subjective metric that attempts to quantify the mental state of someone against the thermal surroundings. Achieving thermal comfort is usually the main drive of the high energy used inside the indoor operations. At a global scale, the building sector accounts for more than 30% of the total energy consumption worldwide. Thermal comfort as a concept relies on various variables such as indoor temperature, clothing insulation, activity level, or metabolic rate. To contextualize the problem at hand, the public schools in Lebanon usually have outdated facilities that serve students with thermal discomfort. At most, public school buildings usually rely on natural ventilation, and there is a great lack of heating, ventilation, and air conditioning system there. It is also important to update existing building stock in Lebanon due to the change in technology and available production tools for different building materials. Building materials and building codes in Lebanon are usually left unupdated in existing buildings, and since most of our building stock in Beirut was built before the 1960s, this leaves various buildings in an uncomfortable state. In order to enhance thermal comfort of a space, the thermal behavior of the space needs to be analyzed. The thermal behavior of a building is captured by several parameters such as the thermal time lag and the decrement factors. Mostly these parameters can be detected with respect to the prevailing climate, as these are very sensitive to transient changes in climate and in a building. Usually under high heat stress or high temperatures, the building will behave differently compared to low heat stress and low temperatures. These thermal variables are usually calculated under very stable conditions inside a laboratory or in such a way to achieve steady state under the building conditions. In order to further understand the concept of thermal time lag and the decrement factor, we can see in this figure that we have the surface temperatures of the wall outside and inside. The change of the amplitude of the sine wave of the temperature curve is representing the decrement factor, or how much a building can attenuate the thermal propagation of the temperature from outside to inside. Also, we can also see that the phase shift or the difference in time when the outside surface temperature and the inside surface temperature peak. This affects greatly when the room will have the highest temperature. For instance, if we are outside at noon and it's 30 degrees outside, inside it may peak like 3 to 4 hours later to have high indoor air temperatures. The energy demand of a building is not only the product of the thermal mass of the walls, it is an interaction between several parameters that contribute into the thermal comfort, such as the building orientation, the materials, the ventilation process, and the windows size, and the tinting and the glazing of the glass. Windows are usually a source of ventilation to diffuse the heat trapped inside a building. However, they are also another source of sunlight and may cause some heat trapping if not dealt with correctly. For instance, there are various literature sources that dealt with optimizing building materials to enhance thermal comfort under passive cooling conditions, such as the study conducted by Hema et al., who studied the effect of compressed earth block and found out that increasing the thermal mass of the wall can greatly decrease the cooling load required indoors. In my study, three historical spaces were studied, and since these are old buildings, the thermal conditions inside the spaces have deteriorated drastically compared when they were first built. Urbanization, different climate conditions, and global warming have all affected the thermal behavior of this wall. This study aims to understand the thermal behavior of classroom spaces in a Mediterranean climate. For this purpose, accurate building energy simulations, accurate building energy models will be built that can be used to further analyze these buildings and propose thermal modifications of those spaces. Two particular questions are addressed in this study. Mainly, how does the thermal properties of sandstone affect the thermal comfort and the thermal behavior of a certain space? The other one is if we can predict unknown building materials, thermal properties such as density or specific heat using computer modeling and experimental data. As a summary for my method, the main application and main interface for simulation is the OpenStudio software, which is an interface for Energy Plus, where we can the input will be the known geometry of the space, the known building materials, and the collected data will be the measured temperature, surface temperatures of the walls, and measured indoor air temperature, along with appropriate recorded climate data. These will be combined in order to calibrate the model. The aim of this step is to make a model that matches the real building behavior under the transient condition or free loading conditions. For this method, I coupled a statistical inferencing algorithm called Bayesian inferencing, and the product of this method will be a valid model that can be used to modify the thermal spaces of the school. These are the model layout or the floor layouts of the four studied classroom spaces. These are named nursery wall of wall 1, the Khalid building, the wall 2, and the wall 3A and wall 3B are both located in Bashura. A little particularity in this study was that this wall here is overshadowed by a massive tree, which leads us to take into account the effect of shading on building energy behavior. This table summarizes the data of the construction data of the studied walls. Practically, what was done is the collected temperature data were used on each marked wall, and sensors collected surface temperatures for each one, and the appropriate appropriate construction documentation was found as follows. All the buildings were built before the 1960s, and they are left untouched since then, and having the need of thermal renovation. The building materials range from sandstone and hollow concrete blocks. As you can compare, sandstone has higher thermal mass of compared to hollow concrete blocks. The building energy simulation consisted of making 3D models on the SketchUp OpenStudio plugin, and associating this model with the appropriate building materials, and noting the unknown construction properties to be further analyzed in a statistical analysis. We can also note that during the data collection period, the COVID-19 outbreak, along with everything that was happening in Lebanon, left these spaces unoccupied, and the behavior of the people and the functional properties such as air conditioning, window operation, or door operation had no effect on the study. This formula here summarizes the aim of this study. The study aims to minimize these two error factors and to match the simulated indoor air temperature with the measured indoor air temperature. As a general calibration standard is that coefficient of variation of the root mean square root error needs to be less than 30%, and the net mean bias error needs to be less than 10%. I'm not gonna go into details into the Bayesian inferencing formula. However, it is a very known formula in statistical analysis and probability, and it relates the posterior probability distribution to a prior and a likelihood. The main focus of the study was the Markov chain Monte Carlo method, which is an algorithm made based on the Bayesian inferencing formula, where we can see that the aim of this algorithm is to generate a probable value of our unknown properties. So if I take an initial guess for my unknown property, which is the density times specific heat, or the thermal mass, I input a general an initial guess, and put it in the model and see how much it is probable by this following likelihood ratio. And if this ratio is greater than a random number generated from a uniform distribution, I can accept this value and continue until the value of the error is minimized. Now, going into the results, this table summarizes all the results of the thermal time lag and the decrement factor. The thing is that we can see the difference between the sandstone and the concrete blocks right away. The decrement factor for sandstone was here, wall 1, wall 3A, and wall 3B, which is somewhat lower than the one in having hollow concrete blocks. Also, with the walls 3A and 3B, which are made of sandstone and have shading on top of them, had the highest time lag, so that if the temperature outside peaks at 12 noon, it peaks inside at 6 p.m. Here is the corner plot of the building energy model and the Bayesian inferencing algorithm. We can see here that we have one unknown variable, which is the density times specific heat of the floor and the ceiling material, which was unknown. We did not have any record of it, and measuring it was very hard because it requires destructive methods. Here, this graph is the unknown variable, and this graph is the known variable, which is the density of sandstone. So we can see here that the output of the algorithm is that the rho 1 C1 of concrete was 1.1 times 10 to the power 6. And rho 2 C2 of sandstone is 0.8 times 10 to the power 6. These peaks represent the most probable solution of the statistical algorithm problem. And we had from the measured data, we had estimated that the ρ2 of sandstone was 0.85 times 10 to the power 6, which is valid against this assumption. So we can say that this prediction of the model was valid. Inputting everything back into the building energy model, we had a 4% CVR MSE and a 3% NMBE, which are very low and valid against the ASHRAE standards. This whole process was repeated for every single space that I was studying, and it resulted in accurate building energy models that had errors ranging from 3.1 to 7.5, which are valid against the standards enforced by ASHRAE. And to conclude, the study tackled the uncertainty associated with simulating old and existing building using Markov chain Monte Carlo method. The MCMC algorithm was used into the building energy simulator Energy Plus. The main goal of this study was to predict the unknown thermal mass of the floor and ceiling material. The problem was validated by comparing the simulated and measured indoor temperature data, and was validated against real inferred thermal properties measurement. And as we can see before that, the errors were low, ranging from 3.1 to 7.2%. In conclusion, the MCMC method was able to help us make an accurate building energy model that can be used to further study the spaces and propose thermal modification of the spaces and accurately predict if we change any part of the building, how it will change in real life. However, further studies can focus on a more general aspect, as the urban climate around the building and other issues can inhibit the accuracy of the model. Thank you.
Thank you, Michel, for your presentation. We can see there is a lot of work done by your slides. We have time for questions. Go ahead, Jennifer.
So, last presentation,
Thank you.
I wanted to ask about the errors you stated previously. Are
Yeah.
they enough to validate and calibrate your model, or are they just convergence criteria used for your?
Usually they're enough for this, for the calibration of the model. However, these are minimum standards, and various variables can put into the equation. So it can be both. No, these are minimum criteria to say that a model can be validated.
So this error compares what to what?
The measured indoor air temperature and the simulated indoor air temperature.
So you actually did measurements. So you
Yeah.
validate your
We did measurement along the whole year of 2020 when coronavirus was outbreaking, and we compared everything with the simulation results.
Go ahead.
Thank you, Zakharia, for the presentation. I just wanted to ask, you mentioned in the title that it's an enhancement for the thermal comfort, but can you correct me if I'm wrong, but I didn't see anything related
Yes,
to
true.
comfort.
True.
Yeah, did you do anything like?
Yeah, it's the continuation of my work on my thesis.
Oh, okay.
Yes.
Okay. So nothing was shown here related to comfort.
Yes,
So
true.
just
The
building
build,
itself.
yeah, it's the model. In my thesis, I proposed some modifications and changes for the building materials or insulation and everything passive ventilation wise. I did not tackle mechanical ventilation.
Thank you.
Other question? I have a comment and a question at the same time.
Yeah.
You have tackling the thermal comfort of building, we can say in Beirut, most of the
Yeah.
and also you have all buildings made of sandstone, which most of the Beirut buildings were made of
Exactly.
Can you tell us more about this, the characteristics of this material from thermal comfort point of view, especially from humidity? Because I used to live in a house, old house in Shafili, where we have a sandstone,
Yeah.
and we had a lot of problems related to humidity.
Yeah, mainly
So
it
did
is
you tackle
not.
this point?
Yeah, mainly this material is very prone to thermal bridging, where the humidity accumulates in specific zones of the structure, and if it's not accounted for in the architecture, it makes wet and humid spots where water can accumulate in it. And no, I did not tackle humidity in my study. It was mostly focused on the temperature and thermal aspect of it.
Could be a good perspective to
Yes, yes, yes.
So as I said, it is an afternoon. Thank you, Michel, for the presentation.